Good afternoon. This file contains the pre-lecture notes for class on Thursday, October 24th. The relevant reading is the conclusion of the Carey textbook, Chapter 9, with regard to the reactions of alkynes. So, we continue our discussion of the alkyne reactivity by talking about the different transformations that the alkyne triple bond can undergo. Two new concepts will be introduced in this pre-lecture, that of the tautomer and that of the poisoned catalyst. A tautomer is a molecule that has more than one isomeric form that differs in the connectivity of one double bond and one hydrogen atom. In effect, we exchange the place of a hydrogen atom in a double bond to create tautomers. We'll take a look at this in detail here in the pre-lecture. A poisoned catalyst is a catalyst that has been partially deactivated by the addition of another substance in order to reduce its reactivity in a reaction. So, on Tuesday, we covered the concept of the acidity of an alkyne functional group in order to deprotonate and alkylate alkynes. Today, we continue with the remaining reactions listed on the slide you see here: hydrogenation, reduction, addition of hydrogen halides, hydration, addition of halogens, and ozonolysis. Once again, you have seen most of these reactions before with regard to the reactivity of alkenes. Remember, an alkyne is just a functional group that contains two pi bonds and a sigma bond. An alkene is a functional group that contains one pi bond and one sigma bond. So, all of the things that alkene pi bonds do, alkyne pi bonds can also do as well. They can just do it twice because there's two pi bonds in an alkyne. We'll go fairly quickly through each of these reactions since most of them have the exact same regioselectivity and stereoselectivity that we've seen when we've talked about addition reactions of alkenes. So, first, you can hydrogenate alkynes in exactly the same way that you can hydrogenate alkenes using hydrogen and a catalyst. Notice what's happened in this reaction. The triple bond requires two equivalents of molecular hydrogen to be fully reduced to an alkane. When we learned about this reaction for alkenes, we needed only one equivalent of hydrogen because we had only one pi bond. Here we have two pi bonds, so we need two equivalents of hydrogen. Your catalyst can be any transition metal listed here. It doesn't matter which one you list as long as it's one of the transition metals. Although you don't need to know the mechanism of this reaction, it's important to note that the reaction is a two-step reaction in which an alkene intermediate is formed. This intermediate comes from the reduction of the first pi bond to produce an alkene. The second addition of hydrogen to the remaining pi bond produces the alkane. On this slide, you can see the sequence of steps that reduces an alkyne to an alkene to an alkane. Notice once again, we require two equivalents of molecular hydrogen to fully reduce the alkyne all the way into the alkane with an intermediate product of an alkene. It is possible to stop the reaction at the alkene intermediate if we use a specific type of catalyst known as a poison catalyst that prevents the alkene from reacting further to produce the alkane. This catalyst is known as Lindlar's catalyst. It's palladium over calcium carbonate. This catalyst, upon addition of hydrogen to an alkyne, will stop the reaction at an alkene. It will not create the alkane. The reason is because Lindlar's catalyst reduces the effectiveness of palladium. In a sense, the palladium catalyst will only work with the highly reactive alkyne, but it's not strong enough to work with the less reactive alkene. Thus, we are able to stop the reaction at an alkene. Notice the stereospecificity of this reaction. Lindlar's catalyst always produces Z alkenes. Here's an example of what this looks like. We have an alkyne functional group up here, plus the addition of molecular hydrogen. We're using Lindlar's catalyst, which we recognize as palladium together with calcium carbonate. We produce our alkene product, and it's in the Z isomer form because we've used Lindlar's catalyst. We can use an alternative reaction, which is sodium reduction, using sodium metal plus ammonia to produce the E alkene. This also is a hydrogenation reaction in which we produce an alkene as our final product. The only difference between sodium ammonia reduction and Lindlar's catalyst is we get the E alkene instead of the Z alkene in our hydrogenation reaction. Here on this slide, we have an example of the sodium metal ammonia reduction of an alkyne. Notice the alkyne functional group up here, combined together with sodium and ammonia, produces an alkene. As seen on the previous slide, the alkene that we produce is an E alkene, where the higher priority groups are on opposite sides of the double bond because sodium and ammonia is stereoselective for E alkenes. The fourth reaction to know is the hydrohalogenation of alkynes. You've seen this reaction before with alkenes. One equivalent of HBr will add across the triple bond to reduce one of those pi bonds to a vinyl bromide reaction. We could also use HCl, which would place a chloro on the vinyl carbon here instead of a bromine atom. Notice that we obey Markovnikov's rule. We add the hydrogen to the carbon atom in the triple bond that contains the highest number of hydrogens on it. Thus, the hydrogen goes to the terminal carbon while the bromine goes to the internal carbon in our final product. Notice what happens if you add two equivalents of a halo acid to an alkyne. Because there are two pi bonds, both equivalents of HF in this case can add across both of the pi bonds to give us a dihalide instead of a single monohalide. The fifth reaction that we'll look at is the free radical addition of HBr. Once again, we've seen this reaction already with alkenes. It does the exact same thing to an alkyne that it does to an alkene. In this case, we add the H and the Br to one of the pi bonds with regioselectivity opposite to Markovnikov's rule. This is exactly what we learned about when we added HBr and peroxides to alkenes. We created alkyl bromides that had a regioselectivity opposite of Markovnikov's rule. So our product in this case would place the hydrogen on the more highly substituted carbon and the bromide on the less highly substituted carbon, using the exact same mechanism that you learned about when you learned about addition reactions of alkenes. Sixth reaction is the hydration of alkynes. You can hydrate an alkyne in exactly the same way that you can hydrate an alkene. One of the pi bonds is replaced by an OH group and a hydrogen. It's the addition of water across the pi bond. The only difference in this reaction is instead of using a 50-50 mixture of sulfuric acid and water, we need a catalyst in order to promote this reaction. The catalyst we use is mercury sulfate together with sulfuric acid and water to produce the addition of the OH and the H atom across the double bond. This product is called an enol because it contains an OH group bonded to a vinyl carbon in a double bond. If you look on the slide, you can see here there is an ene, an alkene, and an alcohol. Put it together and you get an enol. In reality, in the laboratory, we see that the product of this reaction is not an enol, but is instead a ketone is the product of the reaction. We'll take a look at the mechanism by which this occurs. What we should see, though, is that the relationship between an enol and a ketone is a tautomer relationship. Enols and ketones are tautomers of one another. Remember, a tautomer is an isomer in which we've swapped the places of a double bond and a hydrogen atom. We've taken the hydrogen here in the alcohol and placed it over on one of the vinyl carbons and replaced the hydrogen with the double bond that was in the alkene to produce the ketone. Let's take a look at how this works. Enols and ketones exist in equilibrium with each other because they are tautomers and they have a rapid interconversion in acidic media. It turns out that ketones are more stable than enols and predominate at equilibrium, so the true product of the reaction is in fact the ketone and not the enol. The mechanism that explains the conversion of an enol to a ketone can be found on this slide. In acidic media, remember that you have hydronium ions present and available for deprotonation. This reaction proceeds by the pi bond of the enol attacking the acidic proton to produce a water molecule and a carbocation, as we see here. This carbocation intermediate can then be attacked by the resultant water molecule through a deprotonation of the alcohol to produce the ketone final product. A lone pair on the oxygen in water attacks the alcohol proton. deprotonating it to produce the ketone C double bond O. Carbocation in this case is stabilized by electron delocalization, which makes the tautomerization reaction possible. Here we have the two resonance structures produced by the movement of the lone pair of electrons on the oxygen down towards the carbocation to give us this resonance structure in which we have fully occupied orbitals around all of our atoms with a positive charge on the oxygen atom. This is therefore easily deprotonated in order to leave behind a neutral charge on your oxygen atom. Here we have an example of an alkyne hydration reaction. We're combining together an alkyne with sulfuric acid in water in the presence of the catalyst mercury sulfate. Our expected product, of course, is the enol, but don't forget that the enol tautomerizes into the ketone to produce this as our final product via the enol intermediate. Notice that in this reaction, Markovnikov's rule is followed in the formation of the enol. So in cases where we have a terminal alkyne, the OH group would be added to the more highly substituted carbon in the alkyne, thus giving us the ketone as the final product and not the aldehyde. An aldehyde would be produced in any case in which the enol occurred at the end, the terminus of the alkyne, but we obey Markovnikov's rule in this case to form the ketone, not the aldehyde. Here again is the enol intermediate that we would have that produces the final product, which is the ketone. The seventh reaction is the halogenation of alkynes. This reaction is the same reaction you've already seen with regard to the halogenation of alkenes. Notice that we can use two equivalents of molecular chlorine to do a halogenation reaction because we have two pi bonds in the alkyne. Adding two equivalents of chlorine would produce a tetrasubstituted chloride alkyl halide final product in which each of the carbons that were in the original alkyne functional group have been substituted with chlorine atoms that added to the 2 pi bonds. Notice that this reaction has an intermediate product, which is a vinyl dihalide. The addition of the two halogen atoms is anti, as you learned when you learned about the halogenation of alkenes. So for your intermediate alkene, before it goes on to a second halogenation step, would have a E relationship between the two halogen atoms because they came in on opposite sides of the original alkyne functional group. The last reaction that we learned about for alkenes also applies to alkynes. That's the ozonolysis reaction. You've seen this one before. Ozonolysis of an alkyne will cleave the alkyne in exactly the same way you saw that ozonolysis of an alkene will cleave an alkene. But in this case, instead of getting out ketones or aldehydes as your products, you get out carboxylic acids. So note what's happened in this case. We've cleaved the triple bond completely to replace it with a carbon-oxygen double bond. Instead of producing aldehydes or ketones, though, we have OH groups on those carbonyls, which are carboxylic acid functional groups, not ketone or aldehyde functional groups. With reaction 8, that's the last of all of the reactions of alkynes that we've covered to date. They're all listed for you here on this slide. Again, I know it looks like a lot, but don't forget that what you're looking at are all of the same reactions that you've seen before with alkenes. Everything you learned about the electrophilic addition of alkenes applies to the electrophilic addition reactions of alkynes. In each of these cases, there are some slight variations in the reagents that we use due to the fact that we have to catalyze alkyne reactions in many cases, or we want to control the stereoselectivity or stereospecificity rather of the alkenes we produce in intermediate steps, but other than that, everything else is the same. With that, don't forget to review the relevant reading in your textbook and come to class next week prepared to apply what you've learned.